Hello, I'm Andriana Kuhar from Faculty of Electrical Engineering and Information Technologies in Skopje at the University of St. Cyril and Methodius. Today I will be presenting our paper Automatic Detection of Characteristic Segments of a Recorded ECG Signal with Noise Handling Methods by the authors Bojan Glušica, Bojan Aleksovski, and me. Automatic detection of characteristic segments in the ECG signal is of crucial importance for fast and reliable recognition of artifacts that are further analyzed as a means for setting a diagnosis. In previous research efforts that we encountered, segment detection is done using discrete wavelength transform, Hilbert transform, adaptive filtering, etc. for handling the noise within ECG signals, which is computationally expensive. So our goal was to avoid implementation of time-consuming mathematical techniques. ECG signals are sometimes recorded for several days, which results in large quantities of data. Manually reviewing noisy and large ECG recordings by professionals is a time-consuming and ineffective process. This is why we intended to create a fast algorithm for processing long ECG signals. I will begin this presentation by briefly discussing the ECG signal features and noise sources and its influence. I will present in more detail the two techniques we implemented in the developed algorithm for detection of characteristic segments in the ECG signal. In the end, we will graphically observe the results we obtained by implementation of the developed algorithm on ambulatory recorded ECG signals. Electrocardiography is a standard method for recording electrical pulses generated by specialized cells in the right atrium of the human heart. These pulses are recognizable wave shapes in an ECG signal, characterized by their length, rise time, and amplitude. Aberrations in these characteristics usually indicate anomalies in the function of the heart. The ECG signal is formed by quasi-periodic repetition of this typical waveform. Three main characteristic components of the ECG signal are QRS complex, a segment with steep increase in amplitude followed by a steep decrease. It has the highest amplitude of all segments. T wave and P wave, segments with a mild increase in amplitude and longer duration. Why is importance of ECG signal analysis crucial? For example, with proper detection of the QRS complexes, the average heart rate is determined. The length of the QR interval provides information regarding the potential risk of developing lethal arrhythmia. A change in the position of the PQ segment is the most reliable indication of atrial infarction. Some significant factors that produce noise within the ECG signals are movement of skin under the electrodes, interference caused by the power grid, the electrical activity of skeletal muscles, breathing, etc. For reducing the influence of these mentioned types of noise, in the pre-processing section, a bandpass filter with lower limit of 0.667 Hz and upper limit of 50 Hz is applied. It is implemented in order to filter out these types of noise without losing useful information. Further, there is additional filtration with a low-pass filter with a cutoff frequency of 30 Hz. Since the QRS complex also contains higher frequencies up to 50 Hz, this type of filter causes a certain decrease in its amplitude. Tests show that this loss is negligible with regard to the benefits that this kind of filtering introduces in the techniques for segment detection. Apart from filtering, the implemented methods within the algorithm deal successfully with noise themselves, which will be presented in the forthcoming slides. The algorithm for automatic segment detection is written in the free programming language Python and consists of two parts. The first part is finding the R peaks and extraction of QRS complexes with the method of accumulated differential. Because of the steep increase and high amplitude of the QRS complex, accumulated differential is used according to these two formulas. Formula 1, where ECG are the values of the ECG signal and D is the differential, calculated differential. While in Formula 2, A is the accumulated differential calculated as the sum of D over 2m points around the point I, where n is the total number of points. The accumulated differential represents the sum of the differential in a number of points covering approximately half of the duration of the QRS complex. In the right figure, the calculated accumulated differential is shown. In this way, we can detect wave shapes with steep changes and high amplitudes and sufficient duration so that the steep changes as a result of noise are ignored. After we have calculated the accumulated differential, the next step is to set global boundary threshold and local adaptive boundary threshold by determining the greatest difference between two consecutive maxima and minima globally and locally, respectively. The value of the greatest difference is scaled and it represents a minimum boundary value. The points that satisfy this boundary value are candidates to be detected as R peaks of the QRS complex. Because the noise can cause a significant decrease in amplitude of the QRS complex, the previous calculations are repeated locally. The R peak is located by finding a local maximum, after which we proceed to determine the location on points Q and S. Considering the shape of the QRS complex, the coordinates of the S point are found at the local minimum of the original signal in a small area after point R. After that local minimum, we locate a small peak in the next few points. Similar operations are performed for locating the Q point. The second part of the algorithm is detection of P and T waves by tracing their local extrema. In some parts of the ECG signal, noise interference causes the P and T waves to be camouflaged by fast oscillations. However, we can still recognize a group displacement in the oscillations, indicating the presence of P and T waves. This allows us to trace the P and T waves by calculating their local extrema. In this figure, we may observe the oscillations caused by noise. The tracing of the envelope of the noisy signal allows us to bypass the oscillations and greatly reduces the number of checks and calculations that follow. Since there is a possibility that the waves have been distorted as a result of noise, all checks for P and T waves are done between two consecutive QRS complexes, instead around one QRS complex. By analyzing the rise and fall of the values, we can detect the occurrence of the T wave. The existence of the P wave is examined in a similar manner. Developed algorithm was implemented on ambulatory ECG signals with high and medium level of noise from the MIT BIH arrhythmia database, database 1, and MIT ST change database, database 2, respectively. All the figures present results from implementation of the algorithm on signal number 208 from database 1. In these figures, the detected QRS complexes are marked with a yellow line. We may observe the distortion due to noise. It is evident that even in the presence of distortion peaks comparable to the R peaks, the algorithm correctly decides which of them are QRS complexes. The detected and classified segments of the three different types, QRS yellow line, P green line, and T red line, are presented in these figures. It may be observed that the classification here is correct. For verification, the algorithm has been implemented on 5-minute long samples of ECG signals with high noise level from database 1 and medium noise level from database 2. This table shows the average results for signals without hard anomalies obtained by comparison to signals labeled by a cardiologist. It can be seen that the algorithm accurately detects P, T, and QRS segments, and also the borders between them. In some cases, it is 100% accurate, while the lowest level of accuracy is 95%. The small percentage of falsely classified segments is mainly due to the compromise in the criteria for detection in order to process signals rich with noise. And to conclude the presentation, in this research effort, we developed an algorithm by employing a combination of two efficient techniques for detection of peak, URS, and T segments in ambulatory ECG signals. The two techniques are capable of handling the significant amount of noise present in measured ECG signals. The developed algorithm ensures high accuracy and speed at a low computational cost. A 5-minute long signal is processed in 9 seconds. Future research would be focused on upgrading the procedures for noise classification. Ultimately, the algorithm should be modified for detection of segments in real time. And a couple of words about me. I'm an assistant professor at the Faculty of Electrical Engineering and Information Technologies in Skopje. Areas of research, my research interests are numerical methods in electromagnetics, bioeffects of electromagnetic fields, processing of bioelectrical signals, and so on. Thank you for your attention.